Assalamu alaikum. I am Tasim Fariha, a student from the Department of Computer Science and Engineering at International Islamic University, Chittagong. Today I'm honored to present our research on behalf of my other authors. Our paper ID 1250, titled Improving Multifusion Strategies with Modality Interactive Transformer for Emotion Recognition in Conversation. This work addresses challenges in understanding emotions by combining information from text, audio, and visuals. Let's get started. Here's the overview of our presentation. Emotion recognition in conversation is essential for application in human-computer interaction, virtual customer service, and mental health. However, it poses significant challenges due to the dynamic nature of emotional cues across text, audio, and visual modulators. Current models often neglect audio and visual cues or face computational limitations when processing long conversations. Our goal is to address these issues with an efficient model, the Modality Interactive Transformer, MITR, which captures emotional cues equally across modulators, reduces computational overhead, and enhances fusion strategies. Here's the problem we are tackling. Current methods ignore audio and visual cues, focusing mostly on text. They struggle with long conversations that need advanced techniques to process. It's hard to balance the importance of text, audio, and visuals while keeping models efficient. These gaps limit the accuracy of emotion recognition systems in real-world applications like mental health tools and customer service. Our motivation behind this research is to improve real-time emotion recognition in conversation, especially when multiple people are involved. Emotions can be subtle and hard to detect, and combining text, audio, and visuals data often creates challenges in representation. We aim to address these issues and develop more efficient methods that balance these modalities without increasing computational complexity. A major gap in current research is the difficulty in balancing motion cues from different modulators. When one modulator dominates, it can miss subtle emotional difference. Additionally, no existing approach has integrated relative positional encoding with sparse attention for multimodal emotion recognition, which we aim to explore. Our goal is simple. Build a model, MITR, that equally uses text, audio, and visuals. Add an emotional state module to track emotions for each speaker. Ensure the system is efficient without compromising. We looked at existing research to see how others address these issues. While some models improved emotion detection, most still prioritize text or struggle with computational efficiency. This motivated us to design a model that improves multimodal fusion and works better in practical scenarios. Now let me walk you through the methodology behind our research. Here's how it works. We used two datasets for evaluation. I'm okay, consisting 6 emotions, and mailed a conversational dataset with 7 emotions. For feature extraction, we use Divarta for text, Web2Vec 2.0 for audio, and EfficientNet for visuals. To track emotional dynamics, we introduced an emotional state module using layer normalized by LSTMs, which effectively captures speaker-specific emotional state over time. Amateur core's strength lies in its sparse attention and relative positional encoding, which effectively model both intermodal dependencies within modalities and intermodal interaction across text, audio, and visual signals. These features are fused into a global representation, and a softmax classifier predicts the emotion category. Training was optimized with Adam Optimizer using semantic cross entropy loss for noisy labels and emotion shaped loss to account for emotional transition. We evaluated our model using two key metrics, accuracy and WF1 score, ensuring comprehensive performance validation. This is the overall architecture of MITR, which emphasizes both efficiency and accuracy. balancing the contributions of text, audio, and visual cues while minimizing computational costs. On the left side, the comparison table for two datasets shows that our proposed model MITR performs better than other models on both datasets. On IMOCAP dataset, our model achieved the highest accuracy of 74.42%. On the other hand, male dataset, the accuracy we gained 66.60% and WFM score, which is 66.68%, which is better than all the other models we compared. In the ablation study, we tried different combinations of features, and it proves that each part of our model plays a critical role. From the confusion matrix, we can see the model works better on IMOCAP than on MELT. It can easily detect emotions like excited and happy, but struggles with harder emotions like frustrated, where accuracy drops. On MELT dataset, the performance is lower because it is multi-party dataset, and noisy conversation make it harder. The main issues are confusion between similar emotions and the complexity of real-world dialogue, which affects the model's consistency. Here we have the loss curve, which shows how well the model learned during training. The consistent downward trend indicates that the model improved over time without overfitting. This gives us confidence in its ability to generalize to new data. To warm up things, our modality interactive transformer balances text, audio, and visuals to improve emotion recognition. It reduces computational costs and achieves state-of-art performance and benchmark dataset. Future work will focus on integrating more modalities, refining the model for real-time applications, and developing our own dataset for deeper analysis. Thank you for attention. And here are the references we used during our research. These works inspired and guided our study. That concludes my presentation. I would love to hear your questions. Thank you.